So let's just first of all remind ourselves, good morning. About some features of the Poisson distribution, the important features, and then from that we can look at a couple of questions and see how we go from there. Okay, so Poisson distribution then, talk to me about what it is and how we should think about it. So first of all, if we have a Poisson distribution, let's suppose we have some random variable. Now I'm just going to call my random variable x. You can call it whatever you like pretty much, okay? What is the crucial thing that needs to be included in the definition of a Poisson distribution?
Number of tries?
No, I think you're thinking about binomial. So with a Poisson distribution, first of all, so if I say my random variable is distributed using a Poisson distribution, remember we write PO rather than P because we don't want to confuse it with probability. What is the parameter that goes there? I'll give you a clue. We usually call it lambda.
Yeah.
But I'm after what is that lambda? What does it actually mean?
Constant rate,
Good. So there we go. We've got a rate of occurrence, let's call it. Rate of success, rate of occurrence. Okay. So yeah, the parameter that goes here is at what rate is this thing happening at? Now, if we come back to the way which we define our random variable, so I always encourage you when you're dealing with probability distributions, whether it be binomial, whether it be Poisson, whether it be normal, whether it might even be something like geometric or uniform, but although we don't ask those in the exams, although they're on the course when we went through them. But what needs to be included in the definition? So for example, X could be the number of patients which are admitted to hospital, but what's missing from that definition? What needs to be included when I define my random variable?
Time interval.
Good.
Or,
yeah, perfect. So in here, it'll be the number of something. So I'll just write number, or NO for short, of whatever it might be, okay? But then the crucial thing is, it needs to be in some time interval. So whether that be 20 minutes, or whether that be an hour, or a day, it needs to be defined, when you define your random variable, what time interval you are dealing with. Because clearly, the number of occurrences, the rate at which something is happening, is going to be dependent on that time interval.
yeah.
You know, for example, if you're looking at an hour, the rate of success might be 3 things happening within that hour. Well, clearly, if you change the time interval to be 3 hours, there's going to be 3 times as much, right? Good, so that's kind of how the Poisson distribution works. Obviously, if you come to your formula sheets, you will have access to all of the relevant different formulas. So if I scroll down to the second page, which we're looking at discrete distributions, you can see that the first 3, you've got the cumulative distribution function, the expectation, and the variance, is just how to calculate it with some general distribution, okay? And then underneath that, I've created a table which has binomial and Poisson in, which are talking about each of those different parameters. So the the probability distribution function, the expectation, the variance, as well as the parameters in the first column, of my specific distributions, binomial and Poisson, right? So the first 3 are just general for any discrete distribution. The next 2 in that table, although they still follow on from that, they are results which are derived from those 3 particular results. They're specific results there. So you can see there, for example, if you look at the bottom row with Poisson, we've obviously got the Poisson with the parameter of lambda. You've got here that the probability mass function, so f of x, remember that's just the probability that x is equal to some particular outcome, okay, is equal to, and you've got that parameter, you've got that formula there, it's lambda to the power of x, e to the negative lambda, all divided by x factorial, okay? And if you remember, we did actually derive that in one of the asynchronous hours, okay? But also the crucial thing is the expectation. So in other words, what is the mean value? Of course, we don't tend to call it the mean value because we're dealing with a probability distribution as opposed to data, but still nonetheless, we can think about what the expected value should be. Well, in that case, it's just simply the rate of success, right? Because if you're sort of talking about, okay, the number of patients admitted to hospital, for example, in 60 minutes, and we're told that that's distributed with a parameter or a rate of success of 3, so we get 3 patients admitted every single hour, then of course we expect that in that particular time interval that we just get that many patients admitted. Does that make sense?
May I just
Yes?
ask one question? In the first formula,
This one?
what does this formula give us?
Okay, so this gives us the probability of one particular outcome. So for example, if X is the number of patients admitted to hospital in 60 minutes, and if we're told that X is Poisson distributed, let's say with 3, okay, then I can come over here and say, well, if I know that I expect to get 3 patients admitted to hospital in an hour, what if I want to find the probability of getting 4 patients admitted to hospital in an hour? So this is what this formula will give us. Okay, so it's a probability mass function. It tells us, well, look, I expect to get 3, okay, but clearly I could get more or could get less, right? So this will tell me the exact probability based on this particular parameter of getting whatever it might be. So X is equal to 4, or X is equal to 5 patients, or 6 patients. So yeah, it literally tells us what's the probability of getting exactly this many patients admitted to hospital in that time period, right? So yeah, it's a probability function. And clearly as well, just to finish it off, the variance, which is less obvious, it is just lambda. The reason why is a little bit less obvious. If you remember, we kind of did a little bit of derivation in that asynchronous hour, so you can definitely go back and watch that video if you're kind of thinking, why has it got to be that? But it is, okay? Basically, these are the kind of key principles of the Poisson distribution, right?
Variance is also lambda?
Variance is also, yeah, lambda, the rate of success. And again, this is less obvious about why. This makes intuitive sense, right?
Yeah.
This one is less obvious as to why. If you are kind of sitting there thinking, I wonder why that is, I did go through it in the asynchronous hour, okay? So yeah, you can definitely go back and watch that if you want. But it's not strictly speaking necessary, to be honest with you.
Really?
Yeah. I mean, it's there, right? You've got it. You've got it in the formula sheets. Exactly. So you don't need to necessarily derive that in the exam.
Oh. What kind of a class is this?
There's one thing that
I want to learn.
Okay, go for it then. You've got access to that.
So you were talking, sorry.
No?
Yeah, go on.
There's something I remember you were mentioning about proofs.
Yep.
Like in week 3 or 4.
Yes.
We haven't heard that since, but I'm just wondering,
No.
Is it still that, or was it just about the expectation? Or
Yeah. So if you remember, we went through the proof of the expectation of x plus y, okay? Yeah. Why is that equal to the, well no, actually though, this was given to you, sorry. Yeah, good. But then if you remember, we talked about the variance, didn't we?
Yeah.
So we said, okay, the variance of x plus y, that is also just equal to the variance of x plus the variance of y, assuming what?
they're independent.
Good, they need to be independent. If they're not independent, you're going to have a covariance term as well. Yeah, a correlation covariance term, right? So yeah, so this formula was given to you, and I said that proof was technically examinable. To be honest with you, I've kind of had discussions with, leadership team and stuff like that, particularly regarding sort of the nature of open book exams now. These formulas will not be asked in examinable proof in the exam anymore, okay? They were examinable, and technically they're still on the syllabus as examinable, hence the reason why I told you they were. But because you're doing an open book exam, and because it's very easy for you to just turn to that page and just copy and paste, there's literally nothing which I can add or nothing which I can properly assess there. So you obviously need to be aware that they are true, right? And you may be asked to use these results in some way, but you won't be asked to prove them, right? Yeah.
I don't know if there was like another one.
There was one for binomial, I think, as well. Possibly the binomial probability mass function. Yeah, there have been proofs in the course, okay? Generally, like I say, you look at something like that, it's less obvious. Well, there is the reason why, we looked at the reason why in the course, and various other different results and proofs and stuff like that. But as a general rule of thumb, if ever I've said proofs are examinable, they won't be asked in the exam. Technically, they are examinable on the syllabus, but they won't be asked in the exam. Okay. Yeah, exactly. I'll be more asked to use that result in an intuitive or productive way. Yeah. No, absolutely. It's a good question. Definitely a good question. Okay, but does the principle of Poisson distribution kind of make sense? Great, okay. Now, just remember that in an exam situation, I'm less likely to say, hey, do you know what? This is a Poisson distribution question, right? You have to kind of extract that information yourself. So really the key which you are looking for are things which are happening at a constant rate, okay? And you've got some time interval involved, okay? Really, I think there's only two which you need to choose from, Poisson and binomial, right? Binomial has a fixed number of trials and a probability of success. Poisson has a rate of success, right? So no number of trials.